Okay, so having shown you how to use the gravity equation with the circular orbit and all, let me talk a little bit about how to use it when you're near the surface of a body such as a planet. So Newton basically Newton said basically any spherical body, as long as the density was uniform, you could treat it as a point mass with all the mass located at the center. So say here's Dr. Smith or somebody standing up here, and I drop a ball. I want to find out how fast the ball is going to accelerate towards the ground, toward the center of the Earth. So then the ball has some mass m, obviously. So let's find out first what the force on it is, and then we can find the acceleration. So remember that we know which direction it's gonna go, right? We know it's gonna go towards the center of the Earth. So this negative here, if we want to go to magnitudes, we just take off the negative and the r hat, and it's easier this way to go to magnitudes. So let's just use it in scalar form and deal with magnitudes because we know which direction everything's going. So we're going to just say F equals capital G times the mass of the ball times mass of the Earth. I'm going to make that ME just for clarity, and then divided by the distance between the ball and the Earth. Well, we have to measure the center of the Earth. This is what we were told. Basically, is you have to use the center of mass, and if it's a sphere, it'll come out exact. You'll come out with exactly the right answer. And there's a whole calculus proof for why it works out the same. But that's not really what's important. So that's how you find the force, and of course this is just going to equal ma, and in this case the mass of the ball times its acceleration. So I'm going to call this a sub g for acceleration due to gravity. Okay, so now we can cancel out the m's here, right? And what we get is this expression that just says acceleration due to gravity, this is near the surface of the Earth, is capital G times the mass of the Earth divided by the Earth's radius squared. Okay, well that's simple enough, right? So let's plug that in and see what it is using our little power calculator. And I think you guys have kind of a guess what it is, but you might be surprised exactly what comes out. So let's see. G is 6.67 times 10 to the minus 11. Sorry. And we're going to multiply that by the mass of the Earth, which is 5.97 times 10 to the 20, so 10 to the 24th. Okay, and then we divide it by r squared, and the radius of the Earth is 6,378 kilometers. So tack some zeros on the end to make it meters. And there we go. And this should be our acceleration to gravity, which is 9.78 or 9.79. It's pretty close, actually. So acceleration due to gravity is 9.79 meters per second squared. And this is actually tiny bit off from what you might expect it to be. You might expect it to be equal to lowercase g, and it almost is, but there are local variations in the Earth's gravity, for one thing. And there's also the fact that if you're standing on the equator, for example, you've got some rotational action that's going to change the apparent acceleration of the ball. So if I, for example, let's say I'm standing here on the surface, and so I'm going to draw a little blow up, of the picture up there, and here's my ball, and my ball accelerates with an acceleration a. Well, it's accelerating downward, but the thing is the whole Earth is also accelerating downward away from me, right? So that's going to change it a little bit. In fact, that's actually going to make it a little lower, the apparent acceleration, because with the ground accelerating away from you going down, that's going to make the apparent acceleration of the ball go lower. So g is actually going to be a bit less than a sub g. So I'm not sure why I got a slightly higher number. That might be one of these, I might be a little bit off with one of my numbers or something like that. But anyway, that's basically, if you can neglect that spinning stuff, and it's worth, what is it worth? Like a fraction of a percent. If you want to neglect that spinning stuff, you pretty much can. So you can just say g is approximately equal to capital G times mass of the Earth divided by the Earth's radius squared. And that's the relationship between little g and big G. Obviously, if you were standing on a different body, if you're standing on the moon, you use the moon's mass, the moon's radius. That sort of goes without saying. But anyway, that's how to calculate G on, if you want to stand on any planet. I know when I was a kid, I had an astronomy book, it was a kid's astronomy book, and they had a picture of an astronaut standing on Jupiter and being crushed by the 11 or 12 or whatever G's, you feel on the surface of Jupiter. Which is kind of silly, because now, even back then, people knew fully well you couldn't stand on Jupiter, but whatever, that's just what they told us at the time. Anyway, so there you go. That's little g and big G.